Hello everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. And today's topic is one that's very popular, overcurrent coordination and protection basics. And we're excited to see so many people joining us this morning or this afternoon. Before I introduce our guest speakers, as I have a habit of doing, I'd like to run a couple poll questions and get some feedback on where folks stand with the topic. And so we're going to be, if you will, please participate. Obviously, there's no obligation, but it does help our presenters kind of locate the sweet spot, if you will, for the topic. First question, what is your experience level with overcurrent protection studies? This is, as I say, is a popular topic, and I think we have some experts that are going to be sharing their knowledge with us. That looks pretty good. Let's share the results. All right, so there's a little bit of everybody. Good. The next question, which type of overcurrent protection device have you found to be the most challenging? I will mention that we're expecting a Q&A session at the tail end. So along the way, if you have questions, please use the question box to submit your question. We'll try to get to it, time permitting. All right, looks like we've got a quorum here. And here's how people have weighed in on that. Good. And then finally, which is the most common voltage range that you have to work in? We appreciate our guest speakers and try to include a wide variety from different parts of the industry, both in terms of being able to cover a broader, expansive technology, but also coming at the topic from different perspectives. All right, so here's how people have weighed in on this. And again, thank you for participating. And let me get to the introduction of our presenters. These are engineers from S&C Electric. And James Onsiger is a senior engineer in the Power System Solution Business Unit of S&C Electric Company. He has 16 years of combined experience in the electric power and mining equipment industries. His most recent work has focused on performing analytical studies, including short circuit, overcurrent coordination, arc flash, and harmonic studies. These studies are conducted for commercial and industrial customers, as well as wind farms, solar farms, energy storage, and university campus applications. James is a registered professional engineer in the state of Wisconsin. Namrata Arsapota is a project engineer in the Power System Solutions. Sorry, Namrata, for my pronunciation. She's with the business unit of S&C Electric Company and has over 10 years experience as a power systems engineer. Her responsibilities include conducting power systems analysis for commercial and industrial customers in medium to low voltage systems, as well as renewable substations in high to medium voltages. She frequently handles projects that involve short circuit calculations, project device coordination, arc flash calculations, harmonic analysis, reactive compensation studies, capacitor and filter bank sizing, as well as insulation coordination studies and transient and switching analysis. So with that, I'd like to hand the podium over to Namrata. And Namrata, the podium is yours.
Hello, Jim. Thank you very much for the introduction. And you got my name right. Hello, everybody. This is Namrata. And today, my colleague, James Onsiger, and I are going to discuss the basic concepts of overcurrent protection and coordination in electrical networks. The function of overcurrent protection in electrical networks is to quickly detect and isolate faults in order to protect downstream equipment and limit arcing energies. Coordination itself is a state between two series or overcurrent devices wherein the protector devices closest to the fault operate before the protector device upstream. In properly coordinated systems with two overcurrent devices in series between a source and a fault, the device closest to the fault will operate first to trip and is called the protecting device. And the device that is farther upstream would not trip to operate unless the downstream device has failed to trip. This would ensure power outage in the event of a fault is limited to the smallest amount of downstream equipment or downstream customers when the protecting device trips. Let's take, for example, in the event of a fault downstream of one of the outgoing feeders of a panel board. In a properly coordinated system, the load side overcurrent device operates before the protective device at the panel board's main incomer. This ensures that the outage of equipment downstream of the panel board is limited only to the equipment downstream of the protecting device and not the entire panel board and equipment on other unfaulted feeders that would not need to see an outage. In the process of determining overcurrent settings for protector devices, their coordination has to be analyzed, it has to be confirmed. And there are two basic methods for this analysis. One is by plotting the time current curves of the overcurrent settings on graphs. And this would be the most accurate method to determine coordination between series devices. Coordinating TCCs for protected devices ensures that coordination is maintained for all possible fault currents, as we can visibly see that on a plot. The other method of coordination is by using manufacturers' published documentation that tabulate the type of overcurrent devices that can be seen in series based on fault currents. And we do not, these tables are usually published after testing and plotting the TCC curves, which the manufacturers do on their own sites, and they can, and then they publish these tables and which we can use for quick references. Let's discuss these two methods. The first method is TCC, which stands for time current curves. And these are a graphical representation of the amount of time it takes the overcurrent protection to trip and trip its protective device to clear a fault after it has been detected. So what you see here, the logs, what you see here, let me get my pointer. Okay, you can see that this is a log plot with increasing current on the horizontal axis and increasing time on the vertical axis, respectively. And the curve over here is representative of the time it would take for an overcurrent device to time and see the fault and clear the fault. Overcurrent coordination between series devices is studied by plotting these TCCs for each protected device in series within the same graph. And we would stack these curves on top of each other and by adjusting the overcurrent settings. And the device closest to the fault should respond fastest compared to its respective source side device, which should be slower, ideally. TCCs on these plots need to be truncated at the fault current levels available, at the maximum fault current level available in that system, since coordination beyond that point would not be required. The other method of coordination is the coordination tables, as I discussed previously. These are tables released by manufacturers, wherein if we want to do a quick selection of two circuit breakers in series or two fuses in series, then we can use the manufacturer coordination tables. They are developed after testing, and the table, as you can see over here, lists the range of ratings for a type of device, for the type of device. If we have a certain type of source side device, it lists the range of available ratings available for that source side device. And if you want to choose a different type of load side device, then this is the available range of current ratings for the load side device. And the matrix over here shows the maximum current up to which each of these devices can be considered to be coordinated. When we prefer to use this method when there are large number of the same type of devices that need to be coordinated, or when we would want to do a quick sizing of these fuses or breakers, that's when we would use this coordination table method. We, in order to perform an overcurrent study, an overcurrent coordination study, the first step would be to perform a short circuit study. The reason being that we need to ensure that coordination between two series devices is maintained for all types of fault right up to the maximum fault current level expected. There are different types of faults in any system, and each of these type of faults would result in differing current magnitudes, and coordination we need to ensure that coordination covers all of these faults. Additionally, coordination also not only just bolted faults, we also need to ensure that coordination would cover arcing faults also for any of these type of faults. In the following slides, I want to briefly discuss these fault types. The first shown here is the single line to ground fault, and this sort of an event occurs when a short occurs between a phase and a system neutral that is grounded. This is the most common type of a fault that would occur in electrical systems. The path of the fault current is through the faulted phase and the neutral, and there is no fault current in the other two unfaulted phases. So there's no fault current in the other two unfaulted phases. There is, however, a ground fault current component. So the magnitude of a fault current in a single line to ground event is usually lower than, say, a three-phase fault event. Depending on the magnitude and depending on the location of the fault, we may see that the single line to ground fault current magnitude could be higher than a three-phase fault current. That's usually in the event if the fault is near the generator or a transformer which has a solidly grounded neutral. So a single line to ground fault, so that covers the single line to ground fault current. The next type of fault is a line-to-line fault, which occurs when an event occurs that causes a short between two phases. The path of the fault current is through the two faulted phases, and there is no fault current flowing on the unfaulted phase or through the neutral. And the magnitude of a fault current is lower than in a three-phase fault. The other type of fault is a line-to-line to ground fault current. Again, an event occurs that causes a fault between two phases and the grounded neutral, and there is no fault current on the unfaulted phase. And the last type of fault the second last type of fault is a three-phase to ground fault, wherein a fault occurs between all three phases and the grounded neutral. And then we have the three-phase fault, wherein a fault occurs between the three phases of a network. In a symmetrical system, this condition would result in the largest magnitude of fault currents. And when we are doing an overcurrent coordination study using time current curves, using TCCs, the two main faults that we have to analyze and ensure are covered by the TCCs are the three-phase fault and the single line to ground fault. The three-phase fault because it's usually the largest magnitude of fault current that's seen. Once we have completed short circuit analysis and the fault currents are known, the next step would be to select the protective devices. And among considerations like voltage rating, ampere rating of the protective devices, we also need to keep in mind its interrupting rating. The interrupting rating of a protective device is the largest fault current that it can safely interrupt, that it can see and safely interrupt. And this interrupting current rating should be higher than the maximum expected fault currents in the system. So once we have performed a fault study, we need to choose overcurrent devices that have an interrupting rating higher than the fault currents in the system. Interrupting ratings are usually specified in RMS symmetrical current, and they should not be confused with the short circuit current rating of devices. The short circuit current rating is the rating of any electrical equipment that indicates its ability to withstand a certain magnitude of short circuit currents. And that is different from the interrupting rating of protective devices. In the next few slides, I want to go over some of the common types of overcurrent protective devices. The most common type of protective devices in electrical system are fuses. They operate on the principle of a fusible element that is melted by passage of fault currents. And that when that element completely melts, it opens the circuit, isolating the faulted part of the circuit from the source. Fuses are single-phase devices. So each phase has to be installed with its own fuse. And once a fuse has melted, it cannot be used again. It has to be replaced. The common types of medium voltage fuses are current limiting fuse and expulsion fuse. Current limiting fuse has a high interrupting capability. When seeing currents of high magnitude, the fusible element melts fast, with the arcs quickly extinguishing, and it limits the magnitude of short circuit currents through it. The other type, expulsion fuse, the internal arcs that are produced when the fusible element starts to melt on seeing fault currents, those arcs expel gases that result in opening of the circuit. The picture here on the top shows an expulsion fuse with a removable fuse element. That's an external fuse element that can be replaced after a fault has melted the fuse. Expulsion fuse and current limiting fuses are applicable for both high voltage and low voltage and medium voltage applications. I'm sorry. For high voltage and medium voltage applications, LV fuses are the other type of fuses seen on the LV networks. They operate on the principle of fuses melting the fuse on seeing the fault. I would like to discuss what the TCCs, or the time current curves of fuses look like. Fuses look like when we try to plot them on log-log plots. Shown here are some of the common fuses. Some of the common fuses usually available, and their respective time current response. Most fuses have two curves associated with their time current response. The minimum melting curve is the faster response curve, which is indicative of the response when the fuse starts to melt. And the slower curve within the slower curve is the maximum clearing curve, representative of the total time that it will take the fuse to completely melt and clear that fault. Time current curves of fuses are fixed based on their ampere rating, on their speed, on their type, and obviously the manufacturer. Each manufacturer publishes their time current curves for their fuses depending on the ampere rating, and which are commonly available either on their documentation online, and also in several popular softwares. Since fuses are single-phase fuses, each fuse would operate on the fault currents seen on its respective phase, whether it's caused by grounded or ungrounded faults. So whether the fault current seen by that fuse is a three-phase fault or a single-phase fault, as long as the fuse sees fault current above a certain magnitude, it's going to start to melt and to clear that fault. The next type of device are reclosers, which are a self-contained combination of breakers and relays with two sets of overcurrent settings. On seeing a fault, the device would first trip on its faster setting, followed by a reclosing action where the breaker is closed back into the line. This recloser will trip subsequently only if the fault causing the original action still exists, thus preventing extended outages in the event of temporary faults. The determination of overcurrent settings for fast and slow curves for reclosers are determined by the coordination and protective requirements of that specific network, and will need to be decided based on each study. Relays. Now, relays are another commonly used overcurrent devices. Relays with circuit breakers. Relays are programmable intelligent devices that use CTs to detect overcurrents and to trip the circuit breakers in MV and HV applications. Older relays used to be of electromechanical type with adjustable dials. However, newer relays are electronic microprocessor based with digital interface that would help display the settings and which we can use to program the relay. Overcurrent relays have the ability to detect both phase and ground or residual faults, and the location of CTs connected to these relays to detect currents determine whether the relays would need to be programmed for ground faults or residual faults. On detecting overcurrent, the relay times the fault as per its response in the TCC, and it sends a signal to the circuit breaker to trip. Circuit breakers are mechanical switching devices with the capability to make or break currents. When circuit breakers are controlled by relays, they have the ability to interrupt fault currents on receiving the trip signal from relays. I've shown in this slide a plot of the time current curve of an overcurrent relay. Time current curve of relays have a time overcurrent or a 51 element. 51 is the ANSI code applied to the time overcurrent element of relays. And there is the definite time element, which is also called the 50 element of relays. And time overcurrent element is inverse time dependent, and the definite time element is a fixed time response part of the TCC. And while the definite time element shown here has some delay, it can be instantaneous to allow for faster it can be set instantaneously to allow faster operation in the event of a fault above the pickup setting of the definite time element. Relays can have either or both 50 and 51 elements. We can program relays to have either 50 elements or 51 or both. And once fault currents are higher than the pickup setting, it depends on the time in the TCC that the relay will time and trip, and then send the signal to the circuit breaker to trip open to clear the fault. Phase overcurrent elements need to be able to accommodate full load currents while coordinating with series devices upstream and downstream, and its settings and TCC can be adjusted based on these factors. And every relay has its own range of programmable pickup currents, its curve shape, its time multipliers that can be adjusted based on its application in the system. Ground or residual overcurrent elements can be set in relays and can be set differently than the phase element to respond differently for ground fault current magnitudes. Another common type of protective device are low voltage circuit breakers. These are, again, mechanical devices that can be manually switched on and off. And low voltage circuit breakers usually have internal fault detecting and isolating capability. These may have either a thermal magnetic trip unit or a microprocessor-based trip unit, which is also called an electronic trip unit. These pictures over here are some examples of low voltage circuit breakers. The first two pictures show breakers with thermal magnetic trip units, and this last breaker is an example of a power breaker with an electronic trip unit. I'm going to go over the TCCs of what these low voltage breakers trip units look like. The first two curves over here are representative of the thermal magnetic trip units, of what they look like. The thermal response part of the circuit breakers is a time over current response according to the thermal capability, of the bimetal in the breaker. And this area is meant for protecting against overloads, and has a slower response. Whereas the magnetic setting for breakers have an instantaneous response beyond the setting given for the magnetic element. And while the thermal response is usually fixed based on the current rating of the breaker, in some cases, the magnetic setting may or may not be settable based on the make and the type of the trip unit. We can see over here that there appears to be a miscoordination between the two thermal magnetic breakers. However, this question of miscoordination can usually be resolved based on referring to manufacturer's documentation, the coordination tables that we discussed in a few slides ago, wherein the manufacturer would publish which two overcurrent devices can be shown in series, can be put in series without miscoordinating, as there may be a certain amount of current limiting capability in the source side device versus the ground side versus the load side device. So that would need to be analyzed. If ever we see this would need to be analyzed by looking at the manufacturer's documentation. The last curve over here shows the response of the electronic trip unit of low voltage circuit breakers. So apart from the thermal magnetic, there are electronic trip units, and they have adjustable long time settings. Long time setting is responsible for the overload protection in the long time region of the curve, and they have an adjustable short time setting, which would be the short time pickup and the short time delay, and they have an adjustable instantaneous setting for fast response for high magnitude faults seen downstream. Most low voltage circuit breakers can only detect phase faults, but some electronic trip units can be configured to detect ground faults, and they come with a G element for ground faults. The elements, so one thing I did not go over is the elements of the electronic trip unit. The long time is called the L, the short time is called the S, and the instantaneous is called the I. And circuit breakers with electronic trip units can have different combinations of the L, the S, and the I and the G elements based on the type of trip application that we need. I would like to, at this stage, hand over the rest of the presentation to my colleague James Unsager. And thank you, everybody. And yeah.
All right, thank you, Nimrata. So I'm going to continue with the rest of the presentation. So Nimrata talked about different types of equipment and how the TCCs look and how they interrupt faults. I'm going to talk about how they will coordinate with each other. So one good resource to start learning about coordination, if you don't already know some of this, is IEEE standard 242, which is the long title is the Recommended Practice for Protection and Coordination of Industrial and Commercial Power System. And for short, you can call it the IEEE Buff Book. It's part of the IEEE Color series of books, good reference. And it's a great reference for getting started coordinating typical power systems. So this is an excerpt from that standard table 15-3, minimum CTIs, or coordination time interval. And if you look at this chart, you can see there is, on the left side, we've got downstream devices, and then on the right, we've got upstream devices, and the same devices are listed in each. So for example, if we're trying to coordinate a fuse to another fuse, we look at this table, they come together and it says CS. So CS means clear space between the curves. So all we have to do, because again, like Namrata said, the fuses contain a minimum melt and a maximum clearing time curve, and that band, as long as we're outside that band with another fuse, then we're going to be we'll be coordinated. Now this also mentions a little note B here, and that's for adding a minimum melt adjustment for preload. So the upstream fuse may have been either it's loaded heavily, and it recommends adding a slight setback to that, typically 25% in time. You can add to just make sure you won't have any nuisance tripping on the upstream fuse. So you add a little bit more space than the just nominal clear space for that. So that's what that pertains to. Now, so we're going to go through each one of these on subsequent slides. The rest of this table also talks about relays. We've got electromechanical and static relays with their different times. Let's see the next. Okay, so the next one. So first, we're going to talk about fuses. The fuses, like kind of what we just talked about, but again, we have the minimum melt curve and we've got the maximum clearing time of these devices that we want to make sure that the maximum clearing and the minimum melt of the upstream are there's clear space between them. The other thing to talk about that you have to pay attention to is the short circuit of the system, with magnitude of the system that these fuses are in. Namrata talked about that a bunch, but these fuse curves actually go on beyond this cutoff, and they look like they coordinate here, but they could miscoordinate in these higher current regions if the fault current were high enough. Now, in this particular instance, we cut the current off here and there's clear space between here, so we're good to go. These are coordinated. But if you had a higher fault current system, it's be something to look at. Again, and don't go higher than the interrupting rating of these fuses. The other type of fuse we talked about was current limiting, and these fuses also have the same same type of curve. Yeah, sorry about my dog barking. So they have the same type of curve, but they also have another additional term you got to look at is the let-through current, or I squared T. Now, that's kind of a whole nother thing. We're not going to get too much in for let-through current, but if you're coordinating a current limiting fuse with an expulsion fuse, for instance, you don't really have to worry about the let-through current because the expulsion fuse doesn't really care about that. But if you have multiple current limiting fuses in series, that's something you definitely have to look at for your coordination. Next, we were going to talk about low voltage circuit breakers. Namrata did a really good job describing the thermal and the magnetic portions and the long time and the short time of these curves. But again, when we're coordinating together, we're looking for that clear space because we already have this band of tolerance that it could trip in. So as long as we're outside of that, we're going to be coordinated. Then this portion here is often a problem where we have a smaller feeder breaker. For instance, this is a 20 amp breaker and the upstream one's 800 amp breaker, which is pretty big, but they overlap in this instantaneous region. Typically, if this breaker was maybe downstream of this, there'd be a little bit shorter, lower short circuit current here, so this curve might be cut off a little lower, but there's a chance that if you get a fault downstream of this 20 amp breaker, it could also trip this upstream main breaker, which is usually not desirable, but if it's a requirement in the system to be selectively coordinated, and meaning that only this breaker, this 20 amp breaker would trip and not extend, put a higher extent of outage depending on this system. So certain systems per NEC will require selective coordination, and usually you got manufacturers will publish tested devices that even if they overlap like this, they would have tested these two devices if they're the same manufacturer, and they did the testing to say, yes, if there's a fault downstream of this breaker, it will operate and clear the fault before this one clears. So if that's a requirement, then you have to look into that portion and get the similar manufacturers breakers. If there's two different manufacturers of breakers, it gets a bit more difficult to guarantee that. So the next TCC was fuses to low voltage circuit breakers. Now there's two types here. The one on the left shows a low voltage circuit breaker downstream of a low voltage fuse. Now we've got clear space up here in the over in the long time region, and we got short times good. But when we get down here, we have that same problem, that if we have a fault downstream of this breaker and it's a high magnitude fault, it's really high fault current, we could have the fuse could operate maybe even before the breaker, which wouldn't be desirable, or you could have both operate. So that could be a problem. So if you were trying to pick a fuse curve, you might want this fuse curve to come out over here and not interfere with this breaker in the instantaneous region. Alternatively, this right side shows these two nice coordinated curves, but the difference between the left one and the right is the right one has the same low voltage breaker, but actually a medium voltage fuse upstream. To do that, there'd have to be a transformer in between here. Now the transformer would limit the fault current on its low voltage side, but from the impedance of the transformer, and that's where you get this split in the fault current. Through fault current is less on the low voltage side than the higher, so you can get this nicely coordinated setup between the medium voltage and low voltage side of these two in the system. Let's see. Now, I think this is the most requested device that when we did the poll question at the beginning was relays. So how do we coordinate relays to other devices? According to the Buff book, there's again that coordination time interval table. There's a minimum coordination time interval. That means that the minimum means, you know, it's the minimum. There's a bunch of other tables that this table assumes that the device is field tested and calibrated. If it's kind of older and you're not sure if it's been calibrated recently, there's other tables to use that increase these times that you want to set to relays to each other or other devices. But let's take a look at this. TCC has two static relays coordinating with each other. So we've got static relay downstream and we've got static relay of upstream. Now this one says we need 0.2 seconds or 200 milliseconds between the curves to meet this minimum coordination criteria. So here in the instantaneous definite times, we've got 0.2 seconds distance, and then up here we've actually got 1.06 seconds. So that's pretty well coordinated there. Everything's going to be should work out fine here unless something wasn't adjusted right or field calibrated. Then you may want to increase some times just to be sure. Now, if this were electromechanical relays, you can see that if we had electromechanical relay upstream of a static relay, so if this one upstream was electromechanical, you would want some more time in there to make sure that the older style electromechanical relays have time to react if they need to or not react, not to go early. Another interesting point of this is if you see, here's 0.12 seconds, so it's smaller than 0.2, but that's when a static relay is upstream of a fuse. So if this brown curve here was a fuse instead of this relay, there's a smaller, it's 0.12 seconds here, and that reason is because there's negative tolerances on this relay as well, but they don't have to take into account the opening time of the breaker that would be on the right side. So it's just the tolerancing of the relay and CTs that go into that with the time difference for the 0.12. Now, alternately, there's another method that at S&C we like to do is called the graphical relay tolerancing. So so instead of using this coordination time intervals, you can plot the actual tolerances of a relay, including the CT tolerancing, relay tolerancing, and the circuit breaker opening time right on top of the nominal relay curve. There can be times where there's different tolerances between a time over current or an instantaneous or definite time region. So you might have to look at the two different the relay tolerances straight out of the relay manuals. Now, so here we're just looking for clear space between these two devices. So these are the exact same two devices that were here on this plot. same settings and everything. We got the same distances, but it looks a little tighter. It's a little more conservative method, but it takes into account more tolerancing. And you can be sure if you do this method and you use the right tolerancing that you're going to coordinate if you have clear space there, because you took in some worst case tolerances and things. And actually it gets a little better here because it's a less than 0.2 for this particular setup. So at S&C, we like to, when we do coordination studies, we like to use this method, and just to make sure, but not all TCC plotting software can show curves like this. So if you're using a different software or something that can't show that, you can still use the coordination time interval and to be able to coordinate your relays on 2 other devices. All right, so now I'm going to get into some examples of protection of common types of equipment. So the first one we're going to talk about is our cables. So according to the NEC, cables have to be protected in low voltage systems, especially against overload, against there's ampacity tables in the NEC that you would look up based on your application and protect them accordingly. So that's kind of, so our overcurrent protective device has to not be rated higher than the ampacity of that cable to properly protect it. And then there's another portion of the cable we have to protect is for short circuits. So this TCC here is split up into 3 different zones. There's equipment operating area. So this is where it's up to the this example cable's ampacity. So the equipment can operate from 0 to near the max, depending on your design of your system, to operate in the overcurrent protective device won't operate to protect the cable. But and then there's also a cable damage curve. Now this cable damage curve shows if there's a fault current that's higher and longer and above this curve in this cable damage area, you could get damage onto the cable insulation, and the cables can have physical damage to them. So we want to try to protect those cables to those curves. And those curves they change based on the size of the cable and whether the cable is copper and aluminum and what the insulation type is. So you got to know all those parameters of your cable to be able to get this proper damage curve and the ampacity. So the overcurrent protective device, again, needs to operate in this white region here to protect the cable from short circuits and from overloads. Next, I was going to talk about motors. So motors, a lot of motors and a lot of systems. So how do we protect against motors from overloads and faults? So the NEC gives lots of guidance on this about different, according to the application. So there's some special applications such as elevators and fire pumps that are covered other places. Otherwise, this table shows based on percentage of full load current and the type of motor, what the maximum rating is. Now the ratings can be less if it's allowable, but let's take a look at, so a polyphase motor, so a 3-phase motor, and you have a fuse. They want that fuse not to be higher than 300% for the full load if it's a non-time delay. If you want a dual element with the time delay fuse, you can do 175% closer than that nominal full load current. Instantaneous only breaker set to 800 times the full load amp. And we're going to get into these next on the next slide with the TCC a little bit more. And then if you just have an inverse time breaker, it's again 250%. So there's some examples, but it really matters to your application on what exactly type of motor protection is needed. So to plot and for doing a coordination study with motors, here's an example 50 horsepower motor. So here on the blue curve on the left is a typical starting curve that you can plot in TCC programs. This curve up top here is the full load amps that the motor is running at based on its rating. And then there is a motor inrush current that is goes up to here, and in around 5 seconds it cuts down over to the full load rating. So bigger motors, this curve will change shape. Smaller motors, same thing. Just depends on your size and other motor parameters that goes in to determine what this curve is. Now this curve, this protection device here isn't a typical inverse time breaker as we talked about on here, but back to here, what we have here is kind of indicative of a combination motor starter. So your motor starter is not a protective device, and so that just would turn your motor on or off and it'd be full voltage or reversing or something like that. The protection doesn't really matter that much for that, but you have two devices that are protection. So it's your motor overload, which is up here in this green curve, and that comes in different classes. This one, typical class 20, there's class 15, 10, and that depends on just what the shape of this curve is. And then that is set typically 125% over the full load amp of the motor. You may change it depending on your application. You could go off of that previous table we looked at. And also there's a motor circuit protector that is just an instantaneous only circuit breaker, and that is set for that previous table. And that's just set high enough that the motor won't trip on motor starting current. Then you want to be able to protect against any short circuits on that cable. But those are the two, these are two kind of separate devices usually. Sometimes it could be the same, but usually it's two separate devices in an MCC bucket along with the motor starter that you would work together and get these multiple settings set up to protect whatever motor you have. And finally, the last piece of equipment I was going to talk about is transformers. And transformers, again, the NEC gives some guidance on here's a table with maximum rating or setting of overcurrent protection. Now this is the maximum. You could set it closer than this if you can, but if you're looking for different types of fuses or breakers to protect this is the maximum that they can be set. Now this table is split into could be kind of confusing, but if you look at, we've got primary protection over 1000 volts. So if your primary is over 1000 volts, say you've got 12470 kV coming in, 12.47 kV coming in, that would be over 1000 volts, and your primary protection, if you've got a fuse, shouldn't be more than 300% of the full load amps. And if you have a breaker, shouldn't be more than 600% in this particular case. Now, kind of a side note, you may ask, why is the fuse rating half of the circuit breaker? Now, a circuit breaker at this voltage level is probably protected by a relay or controlled by a relay. And if you look back at the medium voltage fuses are actually rated differently than low voltage fuses. If you have a 100E fuse, medium voltage fuse, 100 amps, it actually, the trip of that fuse is actually double that. It's 200 amps. So medium voltage fuses actually, the rate is operates at double its rating. So if you needed to trip at 200 amps and you put a circuit breaker and typed in 200 amps, that would be that was 600% of the transformer you're trying to protect. Again, if you want the same fuse, you have to get half the rating, and that's why that is 300 versus 600. Just a little side note there. Then we look at our secondary protection. Now, if our breaker or if our transformer secondary is over 1000 volts, we've got one set of ratings. So if you're going from, say, 12 kV down to 5 kV or something, that would be for that transformer. And but if it's below 1000 volts, so if you got 480, you've got to follow this column here. Usually they require secondary protection, except for if you're in a supervised location and you have some lower primary protections is a little more restrictive than up here. You don't need secondary protection up to a certain point. There's other NEC considerations for that. But if we get to the TCC for transformers, we've got a bit more to work on than the cables and motors. So what we have here is we got the 3 different zones that we had before. We got the equipment operating area on the left. We've got the damage area on the right. But we also, so when you plot a transformer, you have full load amps of the transformer at the primary voltage, and then you've got transformer damage curves, which represent if there's a fault and the current is higher and exists for this long on the transformer, you could have physical damage inside the transformer to the mechanical workings of the transformer. Now there's 2 curves here. One's a frequent fault and one's a infrequent fault. The infrequent one is higher, so if you can guarantee there's not going to be a lot of faults right in a row, you keep closing in on the same fault, then you can use this higher curve. But if you don't know that for sure, you use the lower curve to the left to protect it. Your overcurrent protective device should be set per that previous table to protect the transformer above its full load amps. Typically, we like to set it around 125% if you can, if it's a relay. But again, it depends on your application, what you need there. The other point that you have to think about for transformers is the inrush point. So when a transformer is energized, it's before it initially has a lot of inrush current that goes through the transformer, and it's higher than the normal operating current. So typically this is a 12 times point of the full load amps at 0.1 second. That's the typical inrush point you'll get in some softwares, and if you do that, you'll generally be okay. Sometimes if you get special transformers, it could be higher or lower, usually lower depending on the design of the transformer. If you can ask the transformer manufacturer specifically what the inrush point is, or an inrush curve, that'll be even better. But again, your overcurrent protecting device has to be set higher than this so you don't get nuisance operations if you were to energize a transformer and you don't want your overcurrent operating there and tripping. So you couldn't get your system up and running. So next I had fault currents through a transformer. Now if you're protecting a transformer, you've got your high voltage side on the, say the higher voltage side, the primary, and you've got your secondary side, and you've got protected devices on each. What are they each going to see? Now this actually varies a little bit depending on the type of transformer connections you have. This diagram shows a YY transformer. Commercial industrial systems don't usually have YYs. They could. Usually you see this in utility and other things like that. But just for an example, if you have a three-phase fault on the secondary side, per unit of current-wise, with the transformer turns ratio, you'll have a same per unit 1.0 fault current on the secondary side that you'll have to coordinate. So this is kind of easy. The same current flows on each side, the same magnitude, just changing the turns ratio. Same with the phase-to-phase fault. If you get, that's 0.87. If you get a line-to-line of the 1.0 per unit of a three-phase, it'll have the 0.87, and it'll again flow in two phases of the primary. And then same thing for single line to ground. You get 1 per unit, which is equivalent to the three-phase around that. And you'll get that to flow in the primary as well. Next, we have delta-delta transformers, which are pretty similar to the YY in terms of this fault current. If you get a three-phase, it'll still have the same magnitude on the primary and secondary. If you get a phase-to-phase, it'll be the same 0.87% and then 0.87% on the primary. Just there's no single line to ground because this is assuming it's an ungrounded system. So if you get a single line to ground, it doesn't just like looks like you got a quarter grounded delta. So there's no short circuit current there. Alternatively, if we look at the delta Y transformer, that's very common in commercial and industrial systems. We've got our, usually it can be a high voltage or a medium voltage delta. And if you have a three-phase fault on the Y side that's grounded, it'll produce the 1.0 per unit current, just like we're used to through here. The difference comes if you have a line to ground fault. So if your overcurrent protection is looking at this 0.87 per unit current here, you have to pay attention to the overcurrent protected device on the primary side, because the secondary side sees this lower current value, but one phase of this delta sees 1 per unit current. So you might have to shift some curves in your TCCs on that special case to accommodate that, to make sure you're actually coordinated, so you don't have a something that could be, say, if you got a fuse in this line, it could actually operate before some secondary side device because of this ratio when you get a line-to-line fault. And then finally we've got the phase to ground secondary fault, 1 per unit here, only 0.58 here, so not much to worry about if you're coordinated on the 1.0 for the three-phase. So finally, I have there's some other overcurrent coordination topics that we kind of touched on a little bit, but we weren't going to really go over here. But for selective coordination, that can be required by code for some systems to ensure that only the nearest overcurrent protected device operates and keeps the outages as small as possible. You look at selective coordination tables from different breaker series manufacturers. Series rating devices, Narada talked about this with short circuit current. If you got a panel, so you got a 10 kV or 10 Ka rated panel, but you want to apply it in a higher rated fault rated system, you could get series rated circuit breakers or fuses that'll protect that panel appropriately, but it takes a bit more engineering to do that. Zone selective interlocking allows you to protect a fast protection of buses and coordination of circuit breakers, but using communications to stop different curves from acting faster, and allows for protection of the bus if it's actually on that bus and not outside down a feeder. And then finally, multiple sources of fault current can also affect your coordination studies. Flowing this current in different various sources can complicate coordination, specifically if you've on-site distributed generation, so generators, PV system, battery systems, and microgrids usually have those issues you got to worry about when you're doing coordination. And finally, that brings up our question slide. I know we're almost done. I think we got time for a few questions, Jim. I want to thank you, everybody, for listening.
Yeah, we do have a handful of questions, and we have limited time. The first question was from Lionel. It says, with present-day numerical relays used on medium voltage and electronic protection on low-voltage breakers, can we still stick to the table 15-3 on the buff book? Is that something?
So that was a question through a transformer?
Yeah, from medium voltage to low voltage.
The low voltage. I would, yeah, there's a difference in the turns ratio and your current, but I would think that it's still the same time between, as long as you got your turn ratios left and the currents are correct, the time is still time. So I would say yes, you can still use that. Maybe double check if there's anything especially in the buff book, but I believe that would be just fine.
The next one is, what should we look for in an I2T when checking current limiting fuses in series?
So each fuse will have a certain amount of let through an I2T that it will, first, so if you have two current limiting fuses in series, that fuse will let the downstream fuse lets a certain amount through. Then you have to go up and look at the upstream fuse, a table, and how much let through current it can, I forget the right exact term, it can withstand before that fuse will start to operate as well. So there's some tables that'll, I forget the exact term, but it will allow, basically it's the amount of current that upstream fuse will allow to pass through it before it in turn starts melting for the I2T. And that can be found in manufacturer's tables.
And then our last question is, what's the difference between the static relay and the electromechanical relay that you had in one of the slides?
I can answer that, but Namrata, do you want to answer any? I don't want to steal all the questions.
Yeah. No, so electromechanical relays, where the relays before electronic relays came into being, they had a dial that could be adjusted, and the electromechanical relays would respond on those dials, whereas electronic relays are programmable relays. They are microprocessor based, and we can control what the pickup settings would be by programming it. So yeah.
So that means we're out of time. Thank you to everyone for attending. Thank you for these good presentations. We're already getting some attaboys or attagirls from the audience. And the questions that we were not able to get to, we will collect in a Q&A response, and everyone will get an email. So appreciate everyone's attention today, and by all means check the EasyPower website for the upcoming presentations. Namrata and James, thank you very much, and we will be talking to you down the road.
Thank you too.
Thank you.